Good afternoon. I'm Thomas Telkamp. I'm working for Global Crossing. As Susan said, the slides on the web might be a little bit different than the version I'm presenting, but just skip the ones.
Oh, it's not just that they're not there. I haven't made the link live yet. Thomas, I'm going to try to get this. I'm sorry. You didn't want me.
Okay, never mind. If you see a slide which is not here, just skip it and the right one will show up. What I will be talking about today is a way to analyze the traffic on your backbone, to learn from what you see and actually try to apply that in the way you plan your backbone and you build your network. It's supposed to be a very practical approach, so anything I'm talking about you should be able, if you run a network, to do yourself. And if you need any help or assistance, then feel free to drop me an email. There's no expensive or complicated hardware needed or any very complicated mathematics or anything. So please go ahead and try this as well. I'll show an example from the Global Crossing network to see how it looks like. The study we've done, of course, has been done over a lot of traces. This should be better than, right? Okay. So I'll just show one example which is representative of what you see on the network. The conclusions are based on a more broader set of measurements. But for anything I show here, although you can do it yourself, your network, if you do it, might be different in scale. For example, this is from an OC48 backbone. If you have an OC12 or OC3 backbone, you will see different things. Also, the SLAs you offer to your customers might be different, the applications you run over your network, etc. So, QoS and backbone networks. Really what that means, or what it comes down to, is low delay, low jitter, and low packet loss. Whatever applications you use, whatever SLAs you offer to your customers, this is really what you want to achieve. Because if these three things are met, then your customers will be happy. And the way, obviously, to do that is just overprovisioning. Make sure your network always has enough capacity to deal with the traffic. Now, I will be using the term overprovisioning several times in the presentation, and there are a lot of different interpretations. So let me be clear what I mean with overprovisioning. I mean enough capacity in the network to deal with the demands, but also in peak times and under certain failure conditions. And the last one is important. So this means if a single link fails, you should still be able to carry all the traffic. And the overprovisioning I'm talking about is the extra bandwidth you need on top of such failure conditions. Obviously, you cannot plan for every failure possible in the network, so something like a single link failure, but then for all links in the network is a reasonable way to start. So what we're after here is to prevent significant queue buildup. Well, Packet Design has been presenting a few minutes ago about measurements they did on the backbone network, and they have clearly shown that overprovisioning works. So there's no question about that. When you measure over a week or a month, you see so less drop packets and so less jitter, so small amount of jitter, that this really works. That's not the problem. But the issue is, and several presenters before me have already referred to that, is that capital is limited today. I mean, if you have the money to build a network which is 10 times larger than the traffic you need to carry, then you're fine. You don't need to listen to the rest of the stuff and go get some coffee or so. But if you're a little bit more restricted on capital and money to operate the network, what you really want to find out is how much bandwidth do I need to provision, how big do I need to build my network to still be over-provisioning, but not too much. That's the question. And so it comes down to these basic rules like upgrade at 50% link load or a maximum of 75% link load in a failure. Are these rules the best we can do, or when you look at your traffic can you actually do better? So the basic question is the backbone traffic well behaved enough to do very tight planning? Obviously this has been looked at before, and funny enough there are kind of opposite views on this topic. One is simulation with a very simple traffic module, which is called the MM1 queuing formula. And when you do that and you simulate how much traffic you can load on a link before you see any significant jitter or packet loss, you see that you can actually load a link to over 99%, like to 99.9%, and still have very low jitter and packet loss. That sounds really great, and it would be good if the internet really worked that way. But if you operate a network, you probably already have the feeling that you can't load your links to 99.9% without any issues. The other view is kind of the self-similarity. So traffic is so bursty that at any time scale, so short time scale, long time scale, is always peaking, and that means you need to provision much more than the average bandwidth you see because the peaks are huge. Also, that just intuitively is probably not completely right. If you look at the link load on a high-speed link like an OC48, it often looks very smooth, so it's not that bursty either. So the question is, where's the truth? It's probably somewhere in the middle, but where? The same as I just told before, but now in the simple picture. On the left, the MM1 queuing formula. On the short term, it's bursty, obviously, because the per session or sessions have influence on the level of traffic. But if you look at the long term, it flattens out. On the other side, the self-similarity. Whatever scale you look at, traffic remains bursty. So what do we do for capacity spanning IP networks? The measurements we have are simple, or most ISPs do that, are 5-minute average or 3 minutes on your links, and that's the data you need to base your decisions on. The objectives you're after are normally 0% packet loss. I mean, you don't plan a network for packet loss. You might not guarantee 0%, but you plan for 0% packet loss, and you want to bound the jitter to a certain amount of milliseconds. Of course, this is an end-to-end guarantee. You want to convert that to per hop. That's a complicated topic and probably a talk in itself, so I'm not really going to touch it here in much detail. In the voice world, they have this nice formula called the Allen formula, and it tells you if you have an average amount of calls in an hour, it tells you how much more bandwidth or how many more links you need to reach a certain blocking percentage, like 1%. So it defines your overprovisioning factor. Unfortunately, for the IP networking, we don't have such a thing. So we have two ways we can go here. We can do mathematical work and try to model the traffic and find the parameters and fit it and simulate. A lot of work is being done on that, and really nice work actually, and they're getting way closer on having a realistic traffic model. But what I'm doing here is much more empirically. Look at the traffic and see what you can learn from it. So it's not to replace the modeling at all, it's just another way of looking at it. So that brings us to the demand characterization itself. We split this in two sides, the long term and the short term. On the long term, that's the measurements you do on your SNMP, your 5-minute measurements. And normally you use something like a P95 over a day or a week to find out how much bandwidth you need. Of course, on the long term, you need to leave a little bit room for unforeseen events like customer turn-ups or changes in peering or whatever, and the growth. So you know how fast the traffic is growing and how much more capacity you need. On the short term, that's your critical time scale for queuing. That's where the queuing happens. So the question is, how much more on the short term do you need from what you measure on your 5 minutes? So what happens within the 5-minute intervals? The picture shows it graphically. The traffic you measure, then sum over provisioning for the long-term variation in growth and your microbursts, the short term on top of that. So first, the long term, what are we looking at? You measure your link utilizations or your traffic matrix, your demands. And the question is, do these graphs look good enough, or is this measurement good enough to do planning on? So what we don't want to see is very peaky traffic or a lot of peaks in the traffic. In other words, not a heavy tilt distribution. This picture, the two pictures over here show an example, just a random example. On the left, you see traffic which is extremely bursty. On the right, you see traffic which over a day is fairly stable. So if you look at the values under that, the left is traffic which is an average bandwidth of 64 kilobits, so that's reasonably low. On the right, you see bandwidth which has an average of 106 megabits, actually. And you also see that the maximum, the minimum, the P95, etc., are much closer together on the high bandwidth and on the low bandwidth. So if your backbone would behave as the picture on the left for all traffic, you would have a real problem in doing any planning. If it behaves like on the right, where you have a clear peak over the day, you could actually do very good planning in your network. So instead of looking at two random samples, this graph looks at all these pairs, all these source-destination pairs between core routers and the network. The exact meaning of the graph is not really important. It shows the variance relatively to the mean. But what I try to show here is that although a lot of demands between core router pairs on the left of the half megabit link are behaving really bad, like on the previous slide, the bursty. So the left graph would represent how the points on the left of the red line look like. The traffic actually, so most of your traffic is carried by the small amount of flows or small amount of demands which are on the right of the link and which actually are behaved quite well, like on the previous slide, the right graph. So without going in detail here, this graph shows that most of your traffic is behaving so well that you can do very well planning on it. That brings us to the short term and actually the more important part of this talk. So what happens within the 5-minute intervals? The time scale which we're looking at here is 1 to 10 milliseconds because that's the kind of time scale where queuing in your routers appears. It's not something you want to do on every link because obviously the data you collect is huge and and it's quite complex to build a setup for something like this. So very simple setup, just a backbone link between two routers. In this case a gigabit Ethernet because that's really easy to monitor. A simple gigabit Ethernet tab, you connect it to a PC and you use that as an analyzer. And as long as you have only a few hundred megabits of traffic, a PC can easily handle that. So no fancy hardware, no complex setup over here. So this is what you get. The traffic on average, so the red line, which is what you normally would measure in your 5-minute intervals, shows an average bandwidth of 225 megabits. But you see, if you look at 10 milliseconds utilization, the peak goes up to 340 and the minimum is 128. So there's a huge spread in the bandwidth you see. But that's not necessarily a bad thing because this is all on 10 millisecond level. So what we first looked at is how the bandwidth is divided. How does the distribution look like? And interestingly enough, it almost is a perfect normal distribution. Again, at the 10 millisecond scale. So what this suggests is that because there are no very large peaks on the right side, so very high utilizations, this suggests that the overprovisioning factor is relatively small, that it's easy to calculate. It doesn't mean everything. Apart from the distribution, you need to look at how are these samples correlated. If you have one very high utilization sample and the next few milliseconds is high again and high again, then you get into trouble. But if you look at 10 milliseconds, and this graph shows, it's a scatter plot, so it shows every pair of consecutive 10 millisecond measurements, and it shows a nice spread. So there are not a lot of packets or a lot of measurements which are both very high. So you don't see a lot of 300 megabit and the next sample again 300 megabits. So all of this really shows that traffic would be extremely smooth and aggregate very well. And unfortunately, the world is a little less nice than what looks from these graphs, because this is all at the 10 millisecond level. So at 10 milliseconds, traffic looks perfect. Now we go to a larger time scale, like 10 seconds. And what you see now, again, same measurement, 225 megabits average, you see that the derivations from the mean are really long. I mean, this line represents 10-second samples. So you see that the maximum is at over 230 megabits, which means that you would need at least 230 megabits to carry this traffic over a link, although your measurements on 5-minute level would show only 225. So on the longer term, like the second level, traffic is really bursty, and you need more capacity than what you can see from your 5-minute measurements. So how do we find out exactly how much more you need? We use the traffic we have measured, and we run it through a very simple queuing simulation. On the left, you have the sample traffic, which you run into the queue. On the right, you empty the queue at a fixed service rate, like 200 megabits, 201 megabits, 202 megabits, and you do that several times. In the meantime, you monitor how deep the queue is, and that way you can find out how much jitter and how much delay you introduce in the traffic. Because we're only looking at low jitter here, packet loss is even out of the question, because that would mean you would fill your queue fully, like 250 milliseconds, and we're really looking at 10 to 20 millisecond scale here. So again, what you do is you run the traffic through the queue, you empty the queue at a fixed rate, and you do that for several different fixed rates. Then you get to this graph, which is kind of the key of the whole story. This graph shows you how much bandwidth you need for a certain delay bound. So the orange line on the bottom shows you the mean bandwidth from the sample I showed before, the 225 megabits. And the other lines show you the bandwidth requirement if you want to comply a certain percentage of the traffic to that SLA. So for example, if we look at the blue line, which is 99%, we can find out how much bandwidth we need if we want to have 99% of the packets have a delay less than 5 milliseconds. And if I look at the graph, it would be somewhere around 240. You can also see that if you have a higher guarantee, like 6 nines, So if only 1 out of a million packets can exceed 5 milliseconds, you obviously need more bandwidth. On the graph you see that when you go to the right and your delay requirements get less strict, the amount of bandwidth you need is much less. Also interesting to see is that when you go to very short or very low jitter bounds, like 1 or 2 milliseconds, your bandwidth jumps up very fast. This is the same as the graph, but just a few numerical examples. For example, a 5-minute delay bound, almost all the traffic needs to confirm, so only 1 out of a million packets is allowed to have a higher delay. The average bandwidth was 225 megabits. The bandwidth you need is 257. That means you need 14% more. On the next slide, I created new traffic from the samples at much higher rates. And what you see happening here is, it's all again for the 5 millisecond delay band for almost all the traffic. What you see is that when the bandwidth goes up, like 600 megabits, which is around OC12 level, or 960, which is around 10 gigabit Ethernet level, or 1.2 gigabit, which is even higher than that, you see that the over-provisioning you need for these microbursts actually gets much smaller. So it goes from 10% to 6 to 5. And when you go to really high speeds, like 10 gigabit, it will go down to really like 1 or 2%, really low. So what do we do with this information? Because just gathering it obviously is not enough. We have seen that the long-term traffic is well behaved, so we know what kind of measurements to do and how to apply them to our planning. We've seen that we can derive this over-provisioning for the short-term dynamics. And what we now do, we summarize the failures we want to plan for. For example, fill every link, every single link in the network, see how the traffic reroutes, and see how much capacity you need. So once you've determined what kind of failure you want to plan for, like the single link failures, you can use this as the input for a simulation tool. So this is an example of a network in a simulation tool. You would feed the demands in here. You would feed the over-provisioning factors in here you have derived. You would run the simulation and it will tell you if your network can carry the traffic or that you need more bandwidth. You can choose to use MPLS routing or IGP optimization to place the traffic where the capacity is, or the other way around. Use the output from the tool to determine where you need to provision your bandwidth in the future. Tools are available. There's a tool called Mate from a company, Carridan, and NPAD from Wendell. So these are just available things in the market today. Very quick note about DiffServe, because that obviously would complicate the whole situation. If you put all your traffic in one class, and there is a certain amount of traffic which needs a higher guarantee than other traffic, you need to conform the whole class, or the aggregate traffic, to that requirement. With DiffServe, if you would put your sensitive traffic, for example, in a priority queue, and give it absolute priority over any other traffic, the whole story I've just told would only apply to the priority queue. When you would deploy any more complex round-robin, weighted round-robin type of queuing, this story obviously gets much more complex. So this is just for, if you do a strict priority queue, the whole story applies to the strict priority queue itself, because it kind of doesn't see the rest of the traffic. So that brings us to the conclusion. This is not some kind of theory of everything with perfect mathematical framework, etc. It's just a simple empirical approach with something you can do yourself and see how it works out in your network. And it proves that you quite easily can find out how much more capacity you need in your network to deal with microbursts. From the example, and actually much more traces than I just showed here, you can see that on a gigabit Ethernet link, you need about 5 to 10% more than what you see on your 5 or 10 minute average samples, SNP samples, to bound the delay to something like 5 milliseconds, which is a really good guarantee for applications like voice over IP or interactive video. It also shows that under a gigabit, this over-provisioning percentage goes up very fast. It gets a really significant percentage. With at higher link speeds, like 2.5 gigabit and 10 gigabit, the over-provisioning percentage becomes really small, and it's something you need to take into account much less than for smaller networks. So many thanks to these people here who helped with all kinds of ideas and scripts and graphs, etc. And also, this story will be written down in a paper in more detail at a later point in time. And that brings me to the questions. feel free to drop me an email if you have any questions later or want to have help or scripts or anything. Okay, thank you. Oh, sorry.
Thomas, just one question. Those over-provisioning percentage rates you were giving, do you think, I personally have the feeling that it's not the case, but do you think that these rates are absolute figures, or that those are relative to the overall network? So for instance, if you are talking about gigabit Ethernet backbone, as of today it might be a fast backbone. In 2 years it will be comparable to what we had with a 2 megabit backbone, for instance, a few years ago. Do you think that these figures will stay at the same value when it comes to percentage of over-provisioning, or if the environment gets faster, then those percentage figures are relative to this environment?
Yeah, they definitely depend on the network as a whole, and the higher the link speeds are, the lower the percentage gets. So on a gigabit Ethernet, this percentage would be higher than it is on a 2.5 or 10 gig backbone. Is that your question?
Not exactly, I think. If you are watching your own network, your backbone, and you are deploying a gigabit Ethernet backbone, for instance. Now, your backbone is relatively high speed for the time of today compared to your direct neighboring environment. Right. If you are not developing this network, and you are there in 2 years with the same gigabit backbone, then the need for over-provisioning, I think, will be higher than today. Why would it be higher than what you see today? Because the traffic, this is based on highly aggregated traffic, so no single application or user has real influence on this percentage. This is thousands of users. Why would the change of traffic, or the mix of traffic change in the future if you're still looking at highly aggregated traffic? I don't know. That was just a feeling. I have not investigated. We'll check it again in 2 years, and then we'll see if it's different.
Well, Thomas, pretty easy. If today you need 500,000 customers to provide you an aggregate of 10 gig, in 2 years you might fill up the 10 gig with, say, 100,000 customers. Okay, so the margins probably will get tighter. Yeah, that makes sense. But also the link speeds will go up as a whole at that time, so it will probably cancel each other out. That makes sense. Yeah. Okay, thank you. Okay.